thank you for inviting me to talk about gaps and needs for ARC observations for offshore wind energy. My name is Charlotte Hasager, and I'm working at the Technical University of Denmark. I'm a professor in offshore wind energy meteorology, and I'm working in the section Meteorology and Remote Sensing. Looking at the needs, we need offshore winds at turbine height. Those data can be sampled from floating lidar buoys or meteorological data from a mast. Other observations are satellite remote sensing of ocean winds and numerical modeling that are typically used to assess the winds offshore. I'm showing here one example of the US East Coast, where we have 25 designated areas for wind farms. And on the right-hand panel, you see the name of the designated areas, and you see the mean wind speeds observed from the satellite SAR data and from the numerical weather model WRF. And what we see is there are, in many cases, quite differences between the two data sets, giving us extra need to check the winds by measurements. A gap in our knowledge is about precipitation that causes blade erosion. In this graphic, we show one that rain and hail will damage the blade leading edge. We know that from testing. And number 3, we would like to have a sensor installed to predict. Now we have rain, and then with 4, we would like to reduce the speed of the turbine so that we could increase the lifetime and also increase the profit. The technologies for nowcasting of rain are from the shorter timescales, nacelle-based LiDAR, or microrain radar, standing say on the ground or on the turbine, large weather radars, or satellite remote sensing of precipitation. In this example, I'm showing a microrain radar data. To the left-hand side, you see a drop falling from the cloud and later hitting the turbine. To the right-hand side, we see the reflectivity observed from the microrain radar and the rain intensity. And we have about a couple of minutes from we observe the rain until we can control the turbine, so that's a sufficient time. In case we do that at sites, I'm showing here how much increase in profit we can do, which is about 1 to 2%. At the same stations, which are coastal stations in Denmark, the lifetime is about 3 years, so that means every 3 to 4 years people will typically repair the blades. At inland stations, the lifetimes are much longer than at the coastal stations due to the weather. We also have an example here on the expected lifetime at a Portuguese station. At the map you see the wind-float Atlantic wind farms off Portugal. They are floating turbines. And if we are assuming ERA 5 model, give us the rain information and wind information, or we can use the Global Precipitation Mission satellite data, we see annual average rainfall. This is during 5 years. And we see the predicted lifetime being about 2 to 3 years. At the land site, the local in situ data gives us a longer lifetime, but we don't exactly know why this difference occurs. So in summary, there's need for wind data at hub height, but we have especially large gaps in knowledge on the precipitation at offshore wind farms.